everybody see their test grade? You can see your test grade. You can also see your overall grade, which should be higher than your test grade because of the lab, 25% lab stuff. I haven't graded all the labs, but the lab grades are probably pretty close to what they'll be. If you did everything and you made an effort to calculate everything, your lab grade should still be just fine. If you skip questions and stuff, it's kind of the only way you're going to lose points. I don't mind doing kind of a makeup points quiz, even though the test grades for this were very, very high. I'm sure you all saw this. There were a lot of 100s. Being such a short test, because I got so hung up on kinetics, I'm really not surprised there were a lot of 100s. Those of you with really low grades, the makeup quiz will probably do a lot to help you. But okay. So there will very likely be more on the next test. More questions, just because I got hung up there. But let's say you got, make this easy. Yeah, let's say if you got a 70 on the test, the makeup points will go, your distance to 100, if it was 70, would be 30 points. And if I gave you 1/3 of that, it might be a little less, then you have 10 points potential to add to your original grade. And so if I gave you the little quiz and you got 100% on the quiz, you get all 10. If you got 90% on the quiz, you get 0.9 times the distance to 100. So it depends on how well you do on the quiz. But we can talk about the quiz and what will be on it and when we'll do it some other time. But it's not going to be like next time, and it's not going to be a pop quiz. I just want to go on with equilibrium for now. We will go over the test. We still have one person that still has to take the test, or a different version of the test. That's either someone who was at a sporting event or was sick. I can't remember which class was which. I'm in the same situation with 1211. So we'll go over the test. I have to wait until I give the test out. Okay. What to tell you about equilibrium, but I didn't say Friday, but I haven't said yet, is if I just wrote the general equation, C plus 1D. So you recognize this. I'm going to put Q here and a C to say this is based on concentration. You put the products on top, C to the X, E to the Y. Okay, you recognize that there is another way to do this. If all your reaction is in the gas phase, I would say Q E. And then you do it by partial pressures. So partial pressure of C to the X, partial pressure P to the Y, partial pressure of A to the N, partial pressure. So if you're given partial pressures instead of concentrations, the brackets with the letter means concentration, you can still work with it. And of course, when it comes to a K, when you get to that special point where it's at equilibrium, you would give KC, and this one I would call K. So we can work with that a little bit. Give you an example. C2H6, C2H4 plus H2. I should have left room for mine. So if this is a gas, this is a gas, this is a gas, then you can do this. You can go Kp equals partial pressure of C2H4. That doesn't have any coefficients in it. So it's just going to be partial pressure of that, H2 over partial pressure of C2H6. And one more little twist that goes with that definition is there is a relationship. You can do the Kp for this gas phase reaction. You could also do it as Kc, concentration of C2H4H2. So when it's gas phase, you can do it either way. So either of those would work, depending on what values you have to work with. But there is this general fact that Kc equals Kp times RT, and there's delta N up here. The delta N is like what we talked about last time. It's the number of moles of gas. So last time I would have said, how many moles of gas are on this side? And you'd tell me 1. And how many moles over here? It'd be 2. And then if you increase the pressure, it would shift this way. If you release the pressure, it would shift that way. The delta moles here is number of moles. Number of moles of gas in the products minus the number of moles of gas in the reactants. Here the reactants have 1, and the products have 2. So here delta N would be 1. So in that case it would just be Kc Kp times RT. Also note we're using a different R in this chapter. This is the one that's in atmosphere liters. And I'll give you that constant on the test. I give you this on the test. I suppose I'll give you those on the test as well. Last chapter we were using moles, joules per mole Kelvin, because we were dealing in energy. This time, when you're talking about pressure, you're talking about atmospheres, and you're even talking about liters. So that's the R you use in this equation. As far as some examples to go through, for some reason I think this is an example from last time. But maybe I didn't calculate one of these explicitly. All right, if you have that, let's do the, that starts off a little long. Let's go do the, let's do the check your learning one for this. 2 SO2. That's 6. That's about all. All right, and it tells you equilibrium concentrations is what I'll call that, are SO2, this is in molarity, it's SO2 concentration at equilibrium, so it matters. It's not an initial concentration or some other concentration. It's concentration at equilibrium. What is the equilibrium constant? These are all gases. But we're going to do it in concentration. The C here means by concentration. The P means by pressures. C means by concentration. And this is, I didn't explicitly do one of these the other day, but it's just solving for this. Products on top, so 2SO3. Concentration of SO3 squared. And on the bottom we have concentration of SO2 squared. And you just plug it in. You see what I mean? I didn't explicitly do this last time, but I've done more with the conceptual stuff. But you're told the concentration of SO3 at equilibrium is 1.1, so you put 1.1 up here, squared. SO2, 0.9 squared, 9O squared. The O2 concentration is 0.35, and you just solve for it. I did it in the spreadsheet a little while ago, but 1.1 times 1.1 over 9 times 0.9 is going to be 0.81 and 0.35. 1.21 divided by 0.81 divided by 0.35. Two significant figures, 2, 2, so I'm just going to keep that. Yeah, 4.3. Already messing up. 1.1 times 1.1, 1.2, 0.9 times 0.9, 0.81. Yeah, it is 4 point. Deal with the units here. Squared. Okay. And this is sort of like what we did last time, but I don't think I did one explicitly like this. This is 13.3. Tell you that K, T, 0.6. In this case, you know K, and then it says, there's several, so for experiment 1, it says, if these were the concentrations, not the equilibrium concentrations, let's say, the concentration of H2O, so if those are concentrations, the question is, which direction, and I'll say left or right. So you're given the K, and you would have to calculate the Q, because it's away from equilibrium. Concentration of CO, there's no coefficients. All right, so CO times the concentration of H2O divided by CO2 H2. I should be able to do that in my head, but I'm not going to try. 020 times 020 and then 0.004 times 0.004. I should put 40 here for the two significant figures. 1, 2, 3, 4, 1, 6. 0 divided by 1, 2, 3, 4, 1, 6 equals 25. So I get QC equals 25. This is what it is at equilibrium. Obviously, it goes from here down to 0.64. The question is, does that mean it's going to flow this way or this way? Someone sets up the experiment with these concentrations and then just lets it go. It's going to go to equilibrium. Is it going to go that way or is it going to go that way? The way I told you to think about it last week was we have products up here and reactants here. And if we're at 25, and we got to go down 0.64, what's happening here to make this decrease? Yep, the bottom gets bigger as the top gets smaller. That means products get smaller, reactants get bigger. That means it's going this way. You good with that? The check your learning is good to practice here. There's a few more examples where you set this up differently. I'm sure one of them is going to have this very, very small 0.000 something, and then it goes the other way. But there's experiment 2 you can look at, experiment 3, and then check your learning. I'm going to do some of these that's related to the gases. Example 13.4. A. Let's do the next one. I already broke that one. CO gas. It's H2O gas. CO2 and H2. Is that what I just had there? They reuse the same ones over and over. Okay, the question here is, equation relating Kc to Kp. So we're working with this now. And really the main thing to work out, because this just means in general, this is just in general, what is the equation? The thing to work out is how many moles of gas here, how many moles of gas here. So what is delta N going to be? N means moles, so what is the change in moles here? This many moles here minus this many moles here gives you the delta moles. Final minus initial gives you the delta. So what's the change in moles here? Zero. There's an invisible one here, so there's 1 mole of this. Invisible one here, 1 mole of this. So we have 2 moles of gas. And I am looking here to make sure that gas is. I've got 2 more gases here. There's no coefficient, so invisible 1, invisible 1. Got 2 moles here. So if you set up that equation, you would go Kc equals Kp R times T. There is a temperature listed here. Oh, no, there's not, because this is general. We'll do one with the temperature next. And if delta T is 0, then everything in this just goes away, because anything to the power of 0 is 1. So in this case, it just reduces down to Kp. And that's the answer to this one. That's the equation that relates Kc to Kp. Let's see. N2 gas plus 3H2 gas same question. So first thing you need to know is what is delta N. So how many moles of gas on the left side? 4 moles over here. 1 from here and 3 from here. And then over here, 0. So it's always final minus initial when you do a delta. So it's 2 minus 4 equals -2. All right, so it's Kc equals Kp RT to the -2. I think that suffices, but they go to the trouble to do this. Kp over RT squared. Maybe that helps if you're doing a calculation. But that's just the definition of a negative exponent. It means you can put it on the bottom and then make it positive. So that's what they did. They did that one extra step. All right, let's do D, where we actually calculate. D gives us, they tell us, let me write the equation. CS2 plus 4H2 gas, CH4 gas, H2S gas. And then they go ahead and tell us that in this case, Kc equals 0.28 equilibrium constant. So what do we do? So it's Kc we're solving for Kp, so we're going to solve for this and then divide both sides by that to get Kp. What's the change in moles here? How many moles on the left side? There's 5. There's 4 there and 1 here. 5 moles. How many over there? So we end up with -3 moles. Oh, sorry. There's a 2 there. how many is on this side? 3. 3 minus 5 equals -2. So this is, change in moles is -2. And I suppose it makes sense to go Kp over RT squared. And then we're just multiplying both sides by RT squared, right? So Kc times. And then we just solve for all of this. We have Kc, R is 0.80206, 0.08206. And they did give us a temperature. Oh, and it has to be in Kelvin. We do need this temperature because there's T here. They give us 900 degrees C. 900 plus 273. I'm not doing 273.15 because this has nothing after the decimal. And that 0.15, it's just going to be a 0.15 down here. And it's just going to go away. And even if we round it, there's still just a 1 there. So even if I did this, I'm going to get the same thing as if I didn't include it. Zero after the decimal, 2 after the decimal. So I'm rounding to here. The 1 does not round to 3, so that's why I just leave that off. So 1173K. So we've got 0.28 times 0.08206 for R times, and that should give us Kp. 0.28 times 0.08206 times 1173. The calculator says 269517864. But we'll be at 2 significant figures, so it's that, so 27. They did it at 1 significant figure. That's right there. 0.28. They rounded this to 3. They did 3. Oh, wait a minute. Oh, I didn't square it. I still think there's significant figures wrong. So I have to square that. 0.08206 times 1173. Six point 68 times 6. I think I'm supposed to keep as many digits as I can here. Not 594. So if I just kept 1 significant figure, let's keep 2. The 9 rounds to 5, 2600, or 2.6 times 10 to the 3. They ended up rounded to 1 significant figure, and the 5 rounded up to 2. So they had 2 times 10 to the 3. They're wrong. No, they don't. They have 3 times 10 to the -5. Oh no. I'm already headed down that road again. I'm just punching it in my calculator, man. myself go through it just to punish myself. Square. If it is KP, KC, RT, -2, it's KC divided by RT squared KC. Yep, okay. 0.8206 times 1173 is that 26 times 96 6. Now it comes out to times 2, 5. That's what my calculator says. Okay. So I had the formula up there wrong. That certainly doesn't help. So now that we actually did a calculation, I realize I have this swapped. Okay, what else to do? So far, we have talked about homogeneous equilibrium. The fancy way of calling it is now heterogeneous equilibrium. There's just one little twist. So if I had, here are the examples. That's a solid PB2 plus aqueous If you have this reaction, maybe you recognize this as what we might call a net ionic equation. So it kind of doesn't matter what the other ions or the spectator ions. You can write a reaction like this because the spectator ions don't really matter. You're just assuming they were soluble compounds. But the key really is if it's S or as a solid or L as a liquid, you don't include those in the reaction quotient. Or maybe I should say the superscript is 0. Maybe that helps. Products here are concentration PB2 plus. It's just a 1 there, so I'll leave it like that. I've got Cl minus. That's got a 2 here, so I'll put a 2 here. And that's over PB Cl2. This is the way we would have done it before. But because it's a solid, I put a 0 there, which makes that 1, which makes all of this just reduce down to equals QC, or equals KC at equilibrium. There are some examples that have L for liquid, so you just cross those out too. How about this one? here's a solid, a CO2 gas. Solid. So there's only one thing here that we're going to include. If I wrote it out, I would go CO2 and products first. That's a solid though, so I'm going to put a 0 on it. And now I'll do the reactants. CaO. That's a solid, I'll put a 0 there. And then CO2, it's a gas, so I'm going to include it, but there's not even a superscript there. So that's a 1, and that's a 1, so we end up with 1 over. Just reduces down to the one thing that's not a solid or a liquid. This is just sulfur gas.
So if it's a liquid, that's one with 0 as well?
Yeah. It's just when it's solid or liquid, you just cross them out.
Okay.
I would say put a 0 just so you get the basic form there, and then you just turn those into 1s and reduce it to whatever it is, just to keep you straight, because it's the exact same formula you're going to write. You just copy it just like that, and then you assume the solids and liquids will have a 0 superscript, which will turn them into 1s. That's just the way I think of it. And then everything collapses the way it should. I think you can get crossed up if you just start trying to eliminate things before you write this. But maybe you can do it in your head. If you're thinking, hey, I could do that in my head, maybe you can. That's a gas that goes on top. No superscript. This is a solid, it's a carbon solid. I'm going to put a 0 there because it's solid. S squared. That's a gas. It's got a 1 there. So all that happens is this turns into a 1, so it goes away. And that ends up being QC. Or KC at equilibrium. You're with me? The liquids show up in acid-base reactions. But we have a whole chapter on acid-base coming up, so I'm kind of skipping over that stuff for now. They really do introduce it too early in this chapter. More of the same. Okay, we are at kind of the famous point. So that's for heterogeneous. I'll move it up there. If you do what we call did you ever hear of ice tables when you took chemistry before? That's an acronym. I means initial, C means change, E means equilibrium. All right, so look at this problem. I2 plus I negative. This is an odd reaction, but it's kind of famous because it goes kind of slow. Didn't our lab use iodine? The kinetics lab we did that took 15 minutes. There's several reactions where this is an intermediate and it makes it take a long time, so it shows up in introductory labs a lot, just because it's not so fast that you can't measure it. So if you have that, and here's the information you have. Concentration of I2, so I could do concentration of I2. It's 10 to the negative 3. That's molar. I just read those off because I find them distracting. So this and this, their initial concentrations. So I means initial. So this is the I. This is what you're given from the initial part. Solution with the concentration is this. Before the reaction gives equilibrium. And then the equilibrium concentration of I2 is given as check the wording again. They didn't state it, but they need to say that. So those are the initial concentrations of I2, I negative, and I3 negative. Initial concentrations. And then it gives you one equilibrium. It tells you at equilibrium, this is going to become this. All right, here's my first question. If you're starting here for this concentration, and at equilibrium goes here, has that increased or decreased to get to equilibrium? I2, I2, initial at equilibrium. You started at initial, it goes to equilibrium. Has this concentration gone up or down? I2. It has gone down. So the ICE table, you do this. C means change, E means equilibrium. And up here you put your reaction I2, Okay, this one's initial concentration, 1.00 times 10 to the negative 3. This one was 1.00 times 10 to the negative 3. And this one was 0. So I've just taken this information and put it in my table, aka my ICE table. And I means initial. Equilibrium concentration for I2. And yeah, it went down. So since it went down, let me put these up here. If this goes down, what's happening to this one? If this is decreasing, then we're shifting that way. So what's happening to I negative? Is it going up or down? If this is going down, that means we're shifting down. So what's happening to this? Let me ask you this. If this is going down, we're shifting this way, what's happening to this? It's increasing. Both of these are decreasing. This one is increasing. You see what I'm saying? If we're going that way, this is going down, then all the reactants are going down. All the reactants have to be used to go to the products. So if this is decreasing on the way to equilibrium, like this is telling you, then you know this is decreasing as well. And this one's increasing. So the point is, the change is, this is going down by some amount. This is going down by some amount. And this is going up by some amount. That's your table. And what you do with that is you go, this with this equals this. Minus some amount gets me to 6.61. See what I'm saying? This has decreased to here by how much? Well, here's the simple algebra that tells you how much. We have a negative sign there to indicate it's going down. So we solve for this. What do I do here? 10 to the negative 4. I've got to go 0.661 times 10 to the negative 3. I suppose you could do it in a scientific calculator. So I moved the decimal one so I can have these the same. And now 1 minus 0.66, is that 0.44?
It's 0.34.
0.34. 0.34?
1 minus 0.66.
Yeah.
Yes.
0.344? 0.34.
Yes, sir.
What about 661? Is it 9? 349?
339.
It's 33. Oh, yeah. Okay, times 10 to the negative 3. So that's x. We did that right? 339. Okay, all right, we'll go with your, because I can't do it in my head. All right. Okay, so the question now is, outline my table better. All right, so this number minus this is going to be this as well. You see what I'm saying? So I'm going to put 6.61. All right, so what goes here? This is positive x. So 0 plus this. So what we just did is find the equilibrium concentrations with the initial concentrations and one of the equilibrium concentrations. We had all this as fact. This is what was given. I don't think they phrased it well enough to tell you this was 0. But that's the information we had. We also had one of these. All right, when coefficients are in here, you put the coefficients in here with your x, but I'll do one of those next. But, oh yeah, there's one more thing. One more thing. Where's the good eraser? Yes. Found all that info. Okay. Question is, what is the equilibrium constant? Or Kc. You can actually straight up calculate it now because you have all your equilibrium concentrations. See what I'm saying? Product is I3 negative. There's no coefficients, so it's I2, I negative. Whatever that comes out to be is this. You're going to do it in your calculator? I could stumble through it. Did I cut it off? What is the equilibrium constant? Oh, it's over there. There it is. Did you calculate it?
Yeah, I got 776.
Yep, that's what they got. The tricky learning one is weird. Alright, where do I go? exercise 13.7. That was exercise 13.7. Now I'm going to do 13.8. All right, this one's a little more challenging. KC equals, that's the equilibrium constant. Into equilibrium concentration for N2 is this, and O2 0.009. So that's for those two. Here's the X. Oh, I thought we used a quadratic formula, but we don't. What we need NO2 here. Okay, well, let me just set it up. Okay, so here's what we have. We have this. We have this. And we have this. I must have cut off I guess I just thought I saw a quadratic. All right, so the point is there's only one variable to look for. So we can actually solve this because they've given us decay. Multiply both sides by these. So just multiply both sides by these and you get this. You with me? You with me? And then square root of both sides. I'll fill in the values. KC is 4.1. Extend to the -4, and then we have 0.036, 0.0089. Anybody want to do some calculator work?
It's 3.6 times 10 to the -4.
-4. So we're taking the square root of that.
Oh, shoot, no, we're taking the square root of 1.31 times 10 to the
Oh, you already figured it out. All right, whatever. You crunch all those numbers and you get what? 3.6
times 10 to the negative 14, sir.
That's the concentration of NO2. So now we can calculate K, or no. What will we do next? Oh, they just confirmed the solution. So that one didn't involve an ice table. I want to do more of these ice table ones. Well, let's go through.
That's an ice table problem. There's still no coefficients, all right. I'm gonna
Have to find more that are really worth doing.
go back to ice tables. This two is
Okay, if it's not at equilibrium, the question is which way is it going to go to get back to equilibrium? And I left out Kp equals 4.50 times 10 to the negative 5. The temperature is 720 K. I don't think you need the 720. All right, so which way does it flow to get back to equilibrium if these are the concentrations? These are the partial pressures, actually.
partial pressure NH3 squared because of that, and then the reactants Pn2 times pH2.
Is that balanced? Yeah, it's balanced. So if we plug these values in,
NH3 is 93, 48 for N2. That's 52 for H2.
what do you get for a value of that? Calculator guy left.
He was doing better than I was. 93 times 93.
0.00128.
Eight, six, four, nine, divided by 48, divided by 1, 4, about 6, about 8. So what you got? 1.28 times 10 to the negative 3. Okay. Compare that to, well, let's put it in. Now compare that to 4.50 times 10 to the negative 5. So did the value of this expression go up or go down compared to equilibrium? I mean, this is where it was when we put it in, and then it went to here to get to equilibrium. So it did go down by a good bit. So if this is going to go down, the bottom has to increase and the top has to decrease, which means we go from reactants to products, which means we go to the right. Follow all that? Towards reactants to reach equilibrium. Good. Any of you guys bring up the PowerPoint that I uploaded this morning? Okay, so I'm at the end of that, and it's got all these from the end of the chapter that you can practice. I'm still dragging my feet on getting on D2L, so start practicing with these. I've got the answers on here too. It's this one, but it's another ice table. They don't have too many. Maybe I just equilibrium pressure. And then I've got release stuff. I want another good ice table thing. I thought I found some.
Are we still going to do lab 5 on Wednesday?
Yeah. If it's scheduled, that's what we'll do. Labs calm down for a while after that, so we can just get through some material. Actually, test one. There's spring break. Yeah, he invented these. There's test two. So we have this Friday, we have Monday, then another lab, and a day in class. I suppose I can put together test two there. It's this stretch at the end where labs calm down. Alright, so maybe it's test three that's going to have them all as usual. But I think we're okay.
So test 2 is after spring break?
Yeah, I scheduled it after spring break. And it's, we have a Monday and a Wednesday, and then the test is that next Monday. And I'm sure I'll lecture more on the 23rd and on the 25th. That'll probably just be review. What am I looking for? I want a good ice table. do some that we did today and then some that we did Friday. Um, 17, and let's just do. Okay, the non-equilibrium concentrations are. Okay. Question is, which direction does it go to get back to equilibrium? That's the equilibrium constant. These are concentrations that are not at equilibrium. We've got 1 for that, 1 for that, and 0. So somebody just put this stuff into the reaction mixture. These are gases too, so it'd be sealed. So which direction is it going? You don't even really need to calculate anything.
So the right.
Yeah. If this starts at 0, and the equilibrium constant is not 0, then it's necessarily going that way. It's too easy. All right. I'll write the concentrations below here. These are all gases. It gives us Kp gives us for NO all right. So these are not at equilibrium. We've got to the second power. So this is where it starts, and then it walks its way to equilibrium, so it decreases. If that's going to decrease, then this has to get bigger and this has to get smaller. So, which way is it going? This is away from equilibrium. This is at equilibrium.
Right.
So if it's going from 4 down to 0.05, it's getting smaller. So the answer to this has to get smaller.
So it's about that.
So reactants are getting bigger while products are getting smaller. So it's going to the left. You guys following this?
Wait, how is it left?
Good. All right. These concentrations they're giving us are not at equilibrium. So they put it in the container and they close it up, and then it proceeds to equilibrium. This is the quotient, but this is the Kp, which is a Q. You with me on that? So that means this gets smaller getting to here. All right, maybe I should write this out. It's the partial pressure of the products in O squared, partial products of N2, partial pressure of O2, QP. We calculated this to be 4, but we know it proceeds down to Kp 0.050. Products and reactants. Simplify the products and the reactants like this to do these. So for something that equals 4 to go down, that means we've got to start there, and this has to get bigger while this gets smaller to get from a higher number to a lower number. You follow that?
Yeah.
We started at a 4 and we needed to go down. So how do we make this go down? We make this bigger and this smaller. That's how we go down. Reactants get bigger, products get smaller, therefore we go this way. Okay, this is reviewing what we did Friday. H equals 95. Might have done this one the other day. Positive 95. All right, the question is, suggest 4 ways to increase the concentration of N2H4. So those are in a reaction vessel sealed up. What could you squirt in there to increase the N2H4 at equilibrium, once it comes back to equilibrium?
You say it all the time.
How do you get more of this once it gets back to equilibrium? You do something to it, how do you get more of this at equilibrium? Think pressure, temperature, and concentrations. What could you do pressure-wise to get more of this? Yes, increase the pressure. There's 2 moles of gas, or 3 moles of gas over here, 1 mole of gas over here. You increase the pressure on it, it'll make it shift towards a smaller, it'll sort of compress what's in it. That's what we did Friday. Your book likes to say, decrease the volume of the container. Same thing as increasing the pressure. if you don't let any gas escape and you press down on it. Picture a chamber with a piston that you can actually push down, the gas can't escape. So increased pressure. What about temperature? Talk about this Friday. I know not everybody was here Friday, but you of course watched the video online on the weekends, right? Those of you who were here, do you remember what we did for temperature? Huh? Well, is it exothermic or endothermic? So, you have reactants and you have products. When it's like that, heat went in and not all the heat came back out, so you had positive delta H there. If the reactants were down here, we'd have a negative delta H. So when energy ends up inside there, it's endothermic. When it's endothermic, which side of the reaction do you put the heat? When it's endothermic, you think of it as you needed to put some heat in there to make it happen. So you put heat over here. I think the more intuitive one is when it's negative delta H. That's a situation where you do the reaction and you feel heat. So heat is kind of a product of the reaction. You've got your products, your chemical products, but you also produce some heat, product, produce. So when it's negative, you produce some heat that comes out of the system, and that's when you put heat over here as if it's a product. That's the more intuitive one, and then it's just the flip side for when it's endothermic. You pretend heat was kind of part of the ingredients to make the reaction occur. What I just described really was the activation energy, though. The energy you put in to make it happen, but at least both of them are going up, so that one's kind of mnemonical, kind of a mnemonic. Okay, if we'll put heat over here, so you're partway there. You're partway back to where we were 4 days ago, 3 days ago. So how do we get more of this with temperature? Huh? What do you do with the temperature? I know there weren't many people here Friday, but y'all are killing me. This is the easier stuff in this chapter. If I increase the concentration of this, which way does it shift? Yep. Watch my body language when I do this. I put more of this in, it flows away, it goes over there. If I put more of this in, it flows away, it goes over there. If I put more of this in, it flows away, it goes over there. If I take some of this out, it flows this way to sort of replace it. If I take some of this out, it sort of flows this way to replace it. If I take some of this out, and it flows this way to kind of replace it. That's concentrations, increasing, decreasing concentrations. But this idea of putting heat over here, you do it exactly the same way. If I put heat in, that is increased temperature, it'll flow that way. So in this case, you want to raise the temperature to get it to flow that way, to get more of this. So we've done pressure and temperature. Pressure was, there's 3 moles of gas over here and 1 over here. So higher pressure will make it compress, so force it to come over here. If you release the pressure a little, or you increase the size of the container, then it's got room to flow out and has more space, so it'll flow that way. And I said, what are 4 things you can do? Well, the other 2 things besides increase the temperature and increase the pressure is add a little bit of this, it'll flow that way. Add a little of this, it'll flow that way. Those are the 4 things. That's kind of a review of everything from Friday. Okay. Okay, good. You obviously need to do more of these. That was number 36. So now we go to 37. that. And delta H equals 92. What effect does increasing the temperature do to the equilibrium? Go through it logically though. Is it endothermic or exothermic? Exo means heat is coming out. Endo means heat is coming in. Endo is plus, exo is minus. So if I don't put a sign on there, it means it's positive. So if it's endothermic, no. If it's exothermic, you can feel heat when you do the reaction. Which side do you put the heat on? You put it on the right side because it's like a product of the reaction. Now the flip side is, if you do a reaction and heat goes in, which side do you put the heat on? Left side. This is a situation where heat's coming in. Negative means you feel heat when you do the reaction. Positive means you're not going to feel heat. You might even feel a little bit of cold because it's taking heat away. So put your finger on the vessel, it's taking heat away from your skin so it'll feel cold. So in this case, heat goes over here. Heat's on the left because this is positive. Another way of saying that is heat's on the left because it's endothermic. Now, raising temperature, which way does it go? Increase this, it'll flow that way. I might have used these very examples Friday, but I did. This one's delta H, negative 285. Is heat going in or heat coming out for this reaction?
It's going out.
Going out because it's negative, so it's like a product. Heat's over here. Increasing temperature will shift it left or right. Increase in temperature, it'll flow this way, so it's to the left. Yeah. So this PowerPoint has some problems and some review problems from Friday. So do look at it. Oh, yeah, let me do this one, because I didn't bring up heterogeneous until today. This is, okay, one more. CO2 gas, H2 gas. Okay. What will the effect be if that's liquid? There's the expression. C is that? No, that isn't, guys. Okay. This is CO. Okay. If I add some C to this, what happens? To this concentration, this concentration, this concentration. If I add this. It's kind of a trick question because remember before where I said, I'll do KC. It's a trick now, but learn it. And I would have put a 0 here to make this a 1 because that's a solid. So that tells you that the concentration of the solid, it's like a solid sitting down at the bottom of a chamber that's got gas in it and it's sealed. If you add more of this, it doesn't affect anything because it's gone now. See what I'm saying? So that's a little tricky, but now it's not because I just explained it. What will happen to the concentration of each reactant and product at equilibrium if you remove a little bit of H2O? Remove a little bit of that. If I remove this, what happens? Which way does it flow? Flows. Remove this, it flows to the left. That means you get a little less of this, a little less of this, a little more of this. And this one's a little tricky because you remove some, and then it starts flowing this way. You got to ask yourself, does it end up higher than it originally was or less? If you remove, it's a little less. If you add, it ends up just a little more. I went through that Friday with those bar graphs. These are easy. The other ones, other than the one you're talking about, are easy. If you remove this, you definitely get less of this and this. And you definitely get more of this. But this, if you remove it, it starts flowing this way and it starts being replaced, but it never quite replaces back to what it was before. So you end up with a little less of that if you remove it. See what I mean? Add some of that, what happens?
Flows left.
Flows left, so you get more. I mean, as soon as you put that in, there is more of these. But then you step back and let equilibrium go, it'll start flowing this way, so you get more than you started with. This one will be less, and this one will just be a little more than there was before you added some of it. Of course, when you add some, yeah, there's going to be more. But that starts to deplete because it starts going this way, but it never depletes below what it was. So it ends up at equilibrium a little more than it was. Oh, awesome. They also tell us the last condition is what happens. It says what happens to the concentration of each reactant product at equilibrium if the temperature of the system is increased. But do remember, when we're playing with concentrations, the value of K or P doesn't change. It's still at that same place on the number line. But when you increase temperature, you end up with a new equilibrium constant. It's a new spot of equilibrium. But that becomes a new constant. And same with pressure, increasing or decreasing. So the flow we're talking about going this way or this way with temperature and pressure, that's permanent. Once it gets up to that new thing, it's back to equilibrium. When you're changing concentrations, it's the changing of the concentration that kicks it away from equilibrium, and then on itself it comes back. When you change temperature, you're changing the equilibrium point. And since you change the temperature, it has to shift to that new equilibrium point. All right, so I want to say increase. If the temperature of this system is increased, knowing this, which way does it shift? To the right, increased. Goes on, yeah, that's right. So if this is negative, its heat comes out, so it's like heat is a product. When this is positive, it's like heat is a reactant. And then you go, okay, heat is over here. Now, increased temperature, I'll flow that way. But it still works the other way. If I decrease temperature, it's like taking heat out, and then it'll flow this way. All right. Look at those problems, y'all, because I'm behind, as usual, putting these on D2L. So I want y'all to practice stuff rather than have it built up on. So just look at these. Make sure you're comfortable with them. Try to be comfortable with them. I'll try to start getting